Okay, all right. Okay, so getting back to holography here. So one thing I mentioned there was that seminar, but they actually postponed it because of the football game. I guess there was problems with parking or something. So whatever. It's scheduled for next Thursday. So I'll keep you posted on that because I think it will be quite interesting for you. Okay, so just a couple of things. So we have a couple of tools now that are available. We have sine theta, the grading equation, sine theta 1 minus sine theta 2 is equal to, say, the order, diffraction order over the period. We'll be looking at this a little bit later for examining another property of holograms and gratings. So again, we have the grading equation. We have, when we form a set of fringes to give us the holographic exposure, the fringes that are eventually copied into the material can also be quantified in the sense of not only the, say, the spacing or period that is set up. So here's K1 and K2, but we can also specify a grading vector K, and that grading vector has a magnitude which is equal to 2 pi over the volumetric period of that grading. So this one here is the kind of the tangential or surface grading component, and so those are different, and although it's a subtle distinction, it's an important one. So again, if we have a set of fringes like that, the grading vector again is perpendicular to that. This again is typically our x direction, and here the z direction. So here is k, and this lambda sub x is along the surface, and again, this whole equation here is kind of giving us a boundary matching or boundary condition, boundary matching kind of equation for matching the tangential component of the electric field, which again is going to give us the directions of the diffracted field. The k vector that we have here, this grading vector, so again, this is the full volumetric period that we have. That's more related to the diffraction efficiency. And so we end up, if we look at our construction here again, we end up with a vector, a nice simple but very useful vector relationship where we have that the difference K1 minus K2 is equal to that grading vector. And this, again, is, we can call it several different things, K vector closure, or it also represents satisfying the Bragg condition, which again, this is you might think of this as a volumetric phase matching condition, which, as we'll see, is going to give us very high diffraction efficiency. And we kind of explored that a little bit last time with this Bragg circle representation of that grading or the Bragg condition or grading vector relation, where here we have K1 and K2. We can kind of write this in form of a circle, and in actuality we can extend this because normally we're going to be talking about in 3 dimensions. So this actually represents a sphere, not just a circle, but it's actually a sphere. And so in many cases, like in some of the work that we're doing in my group, where we use this holographic filtering operation, we need to model this as truly as a sphere rather than just as a circle. turns out, too, that when you model it as well as when you use it in real kind of situations, that the Bragg matching, so this represents the Bragg matching condition. When these propagation vectors that we have truly satisfy the k-vector closure condition, as we pointed out last time, if we look at the diffraction efficiency, say, versus the angle that we may have for these here. So when we are at this k-vector matching condition, the Bragg condition, then we're going to be right at the peak of the diffraction efficiency for that hologram or grating. What's interesting, if you look at this in 3 dimensions, so what we're doing is getting image projections that we select out with these holograms. And so the actual image projection turns out to, if you put it on a plane, you end up getting these spherical, or not spherical, but these curved surfaces. So the spherical Bragg matching condition gives rise to not a kind of a straight line, kind of stripe, high efficiency. So again, this represents the efficiency, say, being equal to 1. And if we had multiple images, like we're multiplexing these holograms, so we get maybe two different stripes here for this hologram, and we end up with, say, another matching condition, which also gives us high efficiency. So again, by looking at this Bragg condition, here we can kind of model what the image should look like when we're trying to see it on a camera. Fortunately, this doesn't turn out to be too much of a problem for us because, we're looking at things at the cellular level, so it's not too distracting to have this curved sort of representation of the image, because we could still see all the features. If we needed to, we could. We actually wrote some papers on this, so we can actually model what that curvature is and do some image processing to pull it out anyway. And it also helps with other types of image processing, because what we want to do is sort of enhance features only within that image plane. And when you have, so you'll have like an image here and an image here from 2 different depths. There's dark regions in between. If you're trying to do image processing, you have these very large changes in intensity, which are hard to maneuver. But knowing what that curvature is, you can kind of pull it out and improve your image processing. Yeah?
So you keep saying images. Are these the fringes that you would be seeing, or is it an actual...
Yeah, so we are, the areas, I should I could draw what we have here. So in our hologram for this, I had a picture of this earlier, but what we do is here's our system. So we're going to have and then we put a lens here, and then there's a camera, and then these are, we end up with images like that. And so what is occurring is we illuminate, we kind of flood illuminate this whole region here. This is, say, a tissue sample here. So we get a depth of volume. This is, again, our Z direction. And we record multiple holograms here. So we actually have, say, 2 holograms multiplexed in there. One hologram is recorded, say, with the with an object point at the focal point, and another one is recorded with that point source shifted by delta Z. Typically, we're looking at cells. A cell is about 20 microns, so we typically shift by differences on the order of maybe 100 microns. 100 microns also corresponds to the kind of the surface layer on tissue, the epithelial layer of tissue. So we can actually probe, say, at the surface, and then 100 microns or 5 cell depths within the surface. And so for this particular application, we're looking at changes in the cell structure in order to see if there's indicators for cancer. Okay, and so the light that then comes from these different regions here. So this will illustrate a couple of other things too. So let me continue here. Let's see. Anyway, I guess this looks more like that. Okay, since we're diffracting in that direction. So light comes from this point here, goes through the hologram. These are, say, at a single wavelength here, and then it gives us an image. Say this one corresponds to the surface here, and this one is at some depth, delta Z. So if we were to illuminate this with a laser, for instance, what we would end up with are just these two stripes. One would, again, correspond to the surface, and the other correspond to the depth region in that tissue. So, you know, a line is not much of an image, right? There's really not much field of view there. But remember what I said, though, is if we, so this is good because it relates back to our Bragg circle. So if we illuminate with another wavelength, okay, then we'll be Bragg matched at a different angle, say theta prime, okay? So instead of illuminating this with a laser, why not, let's try illuminating it with an LED, okay? An LED has a bandwidth that might range, you can get LEDs, you know, anywhere from, say, 5 to 50 nanometers, all right? So now, in order to get high Bragg matching condition, the wavelength has changed, so this length of this vector has changed, and the angle corresponding to that different wavelength has also changed. And so now what happens is for these different wavelengths, you get an increase in the field of view. So now you start to see, you can see an actual scene here. Something like that, all right? So now we can get a field of view with a, say, about a 20 nanometer bandwidth LED. We can get a field of view of about 200 microns. So that's about 100 cell widths in view. So we can see, you know, a reasonable section by using an LED. And again, it all relates back to this idea here. So this very simple idea that we've been talking about has some very important, very useful applications in instrument design and use. Okay, so we'll actually, you know, utilize this again. Actually, I'll go through an example next that in a design problem, so we could see another application of how to use that Bragg circle, or technically, it's really a Bragg sphere. So, so our group has a number of papers on this. If you're interested further, I could, maybe what I'll do too is just, I'll put up a paper on the D2L site if you want to have a look at that. And this is called volume holographic imaging. Or VHI, okay. So again, very interesting, very useful technique. Okay, so what I want to do next is, again, another example of using some of these basic design tools that we have. So the problem that I was starting to outline at the end of the last lecture was we have a substrate and we want to make basically an input coupler. So we're going to come in here with light at normal to that surface, and we want to diffract it at a large enough angle. So we're going to diffract it over at 45 degrees here. And if this were, say, glass with an index of 1.5, that exceeds the critical angle. So we have, again, we have sine theta c is equal to 1, say, in that case. And so, or I'm sorry, 1 over n. And so this works out to be about the critical angle in glass with 1.5 is about 41.8 degrees, something like that. So, so we have basically now what we can do is create or form a waveguide input coupler. Okay, and these are very important for lots of, say, integrated optic devices, communication type devices, and so forth. Okay, so so if we want to use this, say, for a communication problem, we may need to use it at, like maybe 1.5 micron, or in our case, we'll use gallium arsenide at around 850 nanometers. So that's we want that wavelength, and we want that diffraction angle with a normal incident angle. Okay, so that is the problem. So what we want to know is how to design this given the kind of the properties of normal, say, holographic recording materials, which have a sensitivity. In this case, we're going to make this with an argon green line, and so that's a 514.5 nanometer in M. Sorry. So there's 2 humps for an N and 3 humps for an M. Okay, sorry. Okay. All right. So that's the problem. So how to design this with the normal sensitivity range of a material? We might also want to do this in photoresist. We can use photoresist as a holographic grading material as well. That also has, a recording or a sensitivity that's even much lower. It's around 457 is a good recording wavelength for photoresist, which you can get with some diode pumped lasers now. And even there's a couple of argon lines pretty close to, there is an argon line pretty close to that. I've used both for that purpose. All right. So, okay, so what do we have to work with here? So the first step is, again, so we have our desired reconstruction. So we're starting with what we want, and then we're going to work backwards to what we need to make it. So we have the desired characteristics or reconstruction. All right, and so that is, again, we have a 0 degrees and we have a 45 degrees. All right, so we have these 2 propagation vectors, and so here we have a K21. So I'm using the subscript, the first subscript number is 2 because this is in the reconstruction, right? So that's for the reconstruction, and similarly here we have K22 for our second beam that we have. All right. Okay, and we'll also assume that the the incident beam could be inside the medium, although if it's 0 degrees, it's not going to matter too much anyway. All right. So let's. So what should we do next? Well, how about we put this onto a Bragg circle and calculate some parameters. So what we know again is that we have that K22 using our K-vector closure or Bragg condition is equal to K21 minus K. All right, so we can draw this circle representation with some axes here, because ultimately we're going to want to know what's the orientation of these angles relative to our coordinate system. And the coordinate system will define, again, here is say the substrate surface. Which is also, we can say, is along the z-axis, and then this, again, will be, say, the x-axis for our system. All right, so here's the x-axis, and so here, again, K21 is along that x-axis heading towards the origin, and we have our K22 like so. All right, and again, so our grading vector is like this, and so that's K. The fringes again are going to be kind of along the bisector between those two, and so let's draw a bisector that goes through the origin. All right, and so this bisector angle we have as phi. So phi is the bisector angle between those two propagation vectors, and also it's perpendicular, right? It's perpendicular to K. All right. Okay. So what else do we know about this? All right. So, well, first of all, we know that phi, if that bisects 45, is 22.5. So we have some information, more information there. We also know that the propagation vector lengths, since we know the wavelength and the refractive index, so we have K22 magnitude equals K21 magnitude is equal to 2 pi n2 over lambda 2. So n2, this is, say, the index of the recording material. Which we can assume that that's going to be equal to glass, just to make things a little simpler. N2 is equal to N, all right, 1.5. And so with this, so lambda is 850 nanometers, and so this is going to be equal to 11.088 inverse microns. All right, we get the inverse microns from the lambda. And that, again, is the radius of this Bragg circle. We don't have to draw the Bragg circle. We could work, directly from the vector, but sometimes it's a little easier just to, or more visual, just to see it in terms of a circle. It might suggest some other things that may not be quite so obvious just from the simple vector relation. All right, and then we have that if we look at the sine of this angle, right, it's going to be equal to this length over that length, all right? So the sine of phi is, again, we know what that is. It's sine of 22.5 degrees, but more importantly, it's equal to the half the magnitude of the grading vector divided by the magnitude of the propagation vector, right? Because this bisects that grading vector. The angle is a bisector, and so this is also the bisector of K, all right? So we know this, of course, and we know that. So this tells us now what the grading vector is, or I guess I just did half of it here, but K over 2 is now equal to 4.243 inverse microns. Remember, K is 2 pi over the period. So if I asked you for the period, you can also get the period from that number as well. All right? Okay, so now we have the grading vector. We know its orientation, right? It's going to be perpendicular to this ray here, and we know its magnitude. All right? Now, the main thing to realize, right, is that the, bless you, is that the K vector right, is going to be the same during construction, or as a result of the construction and the reconstruction. Now that sounds like kind of a silly thing to say, I guess, or maybe an obvious thing, but it's a very important link, right? Because now we have something that connects what we're going to end up with how we make it. Yeah.
Can you clarify the notation with K21 and K22? So K21 is like the incoming light, and K22 is the diffracted light. Is that correct?
Yeah. So I'm using K21. This is the incident. Reconstruction beam.
Okay. So the first two is for reconstruction.
Oh, yeah. So 2, right, I was trying to make that point earlier. 2, this indicates reconstruction.
Cool, thanks.
And this 2 also is also indicating reconstruction. Okay, and there's just 2 different directions. Okay. Again, that's an important point because we're working the problem backwards. So now what we want is something that is how to make the hologram. So that's during the construction phase. All right. So so we want to now extract the construction parameters. All right. So, well, we know a couple of things, right? We know that lambda 1, for instance, is going to be equal to 514.5 nanometers, and we also have n1. We'll assume is the same as n2, and that's going to be equal to 1.5. And so we have that K11. So now this one means construction, and that's the first propagation vector. And so the magnitude of that is equal to K12, and that's going to be equal to 2 pi n1 over lambda 1. Now, it's possible, and most of the time it happens, that this refractive index actually is different for the material during the construction and after you process it. It's especially true for kind of wet process materials like silver halide film and dichromated gelatin films. They will change their average. This is the average refractive index. And so, again, that will change slightly the orientation of those propagation vectors with respect to that grading vector. And so it's going to it could slightly shift the, and even more dramatically shift the reconstruction angle for optimum diffraction efficiency. Okay? So actually, this refractive index could change quite a bit, maybe as much as 0.1, which is a pretty significant Bragg shift. It'll cause a pretty significant Bragg shift in the reconstructed hologram. All right, so at any rate, so we have this, and this is now going to be equal to, doing the numbers, is about 18.318 microns, inverse microns. So very significantly different from the reconstruction at 850, again scaled by the difference in wavelength. All right, so now let's draw this out. I'll take a clean sheet here to do it more clearly. So here we have our axes. X and X and Z, and so we have that The other thing I need to get to in order to do this is the angle. I want to get the angle here between this angle, this bisector angle again, but this time for this second propagation vector set. All right, so here we'll call that bisector angle alpha. And so this is the bisector angle for the reconstruction. All right, so now we have the same relation that we saw before. We have sine of alpha is equal to the same propagation vector k over 2. So that's why I didn't divide it by 2, or that's why I didn't multiply by 2, because we need that value again. So we have that over k11 magnitude. And this then gives us a alpha bisector angle of about 13.4, 13.393 degrees. Okay, so now let's put all that together. So we have, again, that we have this k vector sitting out here out at a angle of phi, okay, that's perpendicular, that's the ray that's perpendicular to that grading vector. And so that grading vector is sitting there perpendicular to that ray. Here's k, like so. And we also have that, that's not a very good perpendicular. Anyway, stretch your imagination a little. This alpha is going to tell us these angles. So we have alpha and alpha here, and those two angles are alpha, which are, again, the bisector for this new propagation vector. So these lengths here are the k11 and the k12. All right. And so now we kind of have it. All right. So the angles, again, we want it relative to some orientation. So if we take it relative to the z-axis, so we have theta 1 is out to there, and we have theta 2 is out to this vector. Draw that a little more boldly. Okay? And so, so now we can say that relative to that z-axis, we have that theta 1 is going to be equal to, it's equal to 90 degrees plus phi, right? Phi goes to the center. So we're kind of referencing things here to the center. And so we come 90 degrees plus phi, and then we go backwards by alpha, right? So we have pi over 2 plus phi minus alpha, all right? And so, and then for theta 2, we have pi over 2 plus phi plus alpha, all right? So that's where we end up with our angles. And for this case, we have that the first angle is about 99.111 degrees, and the second one is about 125.9 degrees. Okay. So that's what we have, and that's how we can end up doing a design. If in fact, so we're, these angles are a little bit too large. In this case, if we looked at it, this is the surface, right, of the, I'm sorry, z is the surface that we have here. So we should be okay, but in some cases, we may need some very large angles that maybe exceed that 41.8 degrees. I've had this come up a number of times where we're trying to make these input couplers So in that case, you might need to use a prism. So here's the, say, the film or our recording material. If we need to get some very large angles here, so this is a prism, you have to use some index matching oil here. And then you can come in at, you know, an angle here, which if this is, say, 90 degrees, you can come in at larger angles into that substrate, you know, like exceeding the critical angle, because you're now index matched and can propagate through there. And then normally when you do a recording like this too, so this brings up a good point, we'll have to do some absorption here. Usually we use like a black, very kind of a dull black paint on the backside of a cover glass and index match that as well to the glass, so you don't get surface reflections there. So that brings up a good point. If you look on the D2L website, there's I posted lab 1 for you to have a look at. We will probably do lab 1 not next week, but the following week, which I think is the week of September 14th. Next week, I'll go over the lab and we'll kind of set up the lab groups. So you might want to think about it now, but the way I kind of like to run the labs are that we divide up into maybe like 2 groups or possibly 3 groups, and then we'll have 2 or 3 sessions come over to my lab over in ECE, and we'll just sort of decide upon a good time, you know, like Tuesday morning or Thursday morning or Wednesday morning or afternoon or whatever kind of works. But I'll kind of take a straw poll one of the days next week. So just think about when you might have, say, a 2-hour period that's free, and then, you know, and have maybe 2 options in case, you know, the one fills up or nobody else is there, and then we'll just meet over at ECE during that time slot and run through the lab. But the nice thing about the lab is you'll kind of learn how to do things like this, all right, and see, you know, the importance, say, of index matching, or if you need to do some prism coupling or what have you. So we have a number of fun labs kind of planned and very instructive as well. So, okay, so that's kind of the basic. That's a nice design problem, and you know, it accomplishes a very useful thing. You know, making an input coupler is quite useful. A number of gratings are made holographically for lasers, for making distributed feedback lasers, for fiber Bragg gratings. So you now have the tools to you know, to kind of do all those homework problems, but also to actually do some fairly interesting and important applications. Okay. With regards to the homework, did anybody have any questions on the homeworks? It's up there. Basic problems are, again, so here, just quickly run through these, maybe outline what to do. So here I am telling you that there is a refractive index, so in some of these cases you're going to have to do a Snell refraction into the medium. And you can see there's a couple of different designs here. Here's the beams are counter-propagating like that, so what kind of grating is that?
The vertical.
They're vertical, but is that reflection? Yeah, and actually that's an unslanted reflection, okay? Here's another one where they're counter-propagating. This one's going to be a slanted reflection grating, okay? And so, again, just doing a couple of calculations there for that. And then here I have several questions on this kind of holographic lens setup. So the first part is to do some calculations for the grading vector in these different locations along the aperture, and then to use the grading equation to determine the number of different diffraction orders that you might get from these different regions on that aperture. Okay. Notice that the angles are different. Remember, the angles are inversely related to the period. So you're going to have a very small period here, a very large period there, or a relatively large period there. All right. So start to try to intuitively think about that. It'll help you in doing problems and analyzing different situations. And then this one here, we wanted to form a fiber Bragg grating. So again, this problem is, we talked about it before a little bit. So you want to use this in a case where we want to make a reflection grating. So this reflection grating is going to work at the 1535 nanometer, where we have light coming in and coming out. So the period and so forth has to be designed for that. But we want to make it using a transmission geometry like so. And this is at 244 nanometer, where the glass is sensitive. Okay, so that's kind of the basic outline. And then you can use some of the things that we just went over to kind of run through that design. Okay. All right. Good. Okay. So the another thing I want to talk about. So we're still on the introduction of the and terminology kinds of things, but another very important aspect of holography and gratings in general is that of dispersion. And dispersion is a very important feature of gratings, and it indicates a strong relationship between the diffraction angle and the wavelength. Okay, and we're going to see this time and again when we talk about holograms and gratings throughout the class, that there is this very strong dependence on these two, and it's both a blessing and a curse in a sense that a lot of times it keeps showing up and we really could want to get rid of it. Like in imaging, for instance, if you're making a holographic lens, you really you don't want a lot of chromatic aberration in that lens. It's sometimes very difficult to get around. But in other cases, you want to maybe separate the spectral components, so it's a tool that you can use quite readily to accomplish that. All right. So there are a number of different dispersion relations that occur in holography, and so far, we've been talking about the thin gratings, which are described using the grating equation. So let's first look at the grating equation and see how we can pull out a dispersion relation. All right. So we have sine theta 1 minus sine theta 2 equals lambda over the period. We'll just worry about the first diffraction order for now. And so, what if we add a little bit of a, so here's our grating here, and we come in at some angle here, theta, say theta 1 and theta 2. And then what if we change this angle a little bit? What happens in our reconstruction? All right. Well, if we change the angle a little bit, the phase matching condition changes, and we can represent that as again, the only other thing to change here, if these two are fixed, theta 1 and theta 2 say are fixed during our construction, and then we use one of these during the reconstruction. We change one of those angles. The only thing that can change is that wavelength. All right. So if we have, say, a slight change in theta 1, so we have theta 1 plus delta theta minus sine theta 2, this is going to give rise to a lambda plus delta lambda over the period. All right. And so if we kind of expand this a little bit, we end up with a sine theta 1 cosine of the delta theta plus cos theta 1 sine of, delta theta. And that's going to be equal to lambda over the period plus the delta lambda over the period. All right, so let's say, again, so here's, oh, yes, sine theta minus sine theta 2. Sorry. If let's say this is our delta theta here, let's make delta theta small, so delta theta is, say, much less than theta 1 or theta 2. Then in that case, this is about equal to 1, and this is about equal to delta theta. All right. So then we could say that we have sine theta 1 plus the cosine theta 1 delta theta minus sine theta 2. Let's not forget that this time. And that's equal to lambda over the period plus delta lambda over the period. Okay, well, notice now that here we have the grading equation, right, in there. So basically we can drop that out, and what we're left with is the dispersion relationship for the thin grading. So we have again cosine theta 1 delta theta is equal to delta lambda over the period, and the dispersion relationship is equal to a change in the angle with some change in the wavelength. And this is essentially, again, with our approximations that we made for delta theta and so forth, this is just equal to 1 over cos theta times the period. Okay, so this is the dispersion relationship for a thin grading. And notice that cosine theta is a fairly slow changing function of angle. So really it's a function of this delta theta delta lambda is we can think of this really as being a function of just the inverse of that period, right? Kind of makes sense, right? If we make that period really small, okay, we should see some very large changes in the angle for a given delta lambda. A lot of dispersion, right? Because we have this very fine feature. If we have a very coarse feature, we don't expect to see too much spreading of the wavelength, all right? And this, again, is kind of related to something which we'll talk about shortly, and that's the Fourier transform kind of characteristics. We have a spatial frequency, essentially. This 1 over the period is the spatial frequency of the grading, right? And this is kind of a spatial change. The theta is a spatial change. If we put a lens in it in the system and multiply by delta, or use delta, have a delta theta incident, if we go out at the focal length, we're going to see some delta x change in the position. So this is kind of a position or space or spatial kind of characteristic, whereas this is a spatial frequency characteristic. And so these two are interrelated, and there is a close relationship to kind of the Fourier transform descriptions of things that occur in propagation. Okay. All right. So this so the dispersion relation that we have for the thin grating is actually, it's going to be the meaning of it and so forth is going to be quite a bit different from the volume grating or the thick grating. We'll talk more about the thick grating later, but what I thought I would do now is give an example of this dispersion, which again is very useful. Even at this stage, we can use it in describing some very important applications. And so we'll look at an example of making a spectrometer using a hologram. All right, so here again, so we have a hologram like so. We'll draw our optical axis like that. And so we'll have a hologram that has, say, 0 degrees and 30 degrees. So we're going to illuminate this, again, off axis like so. And then our diffraction direction here is going to go in the direction, say this is K1 and this is K2. The direction of diffraction is going to go in this direction, all right? And so now, though, we'll illuminate this with, say, lambda 1 and lambda 2. So we have a spectrum, but basically it's just two wavelengths, all right? So how can we make a spectrometer out of this? Well, we can do that by putting a lens here. And, of course, the lens has a focal length. Whoops, like that. And so first, if we just look at one wavelength, say the design wavelength for this grating, because one of these wavelengths is going to go off, right, at, say lambda 2 is going to go off at a direction. But let's look at lambda 1 for now. And so lambda 1 is going to come to focus there. So we have a focal length, and we put some, of course, we're going to have some aperture size too. All right. So what we'll see here, and again, if you're an ECE student, may not be too familiar with this, I'll briefly go over this later, but you get a diffraction spot. Okay, so we're not going to talk about aberrations. We have a diffraction limited lens. So we're going to get some spot there. It's not an infinite resolution. It's not going to give you a point. There's some limit to that size, which depends upon the limit of that aperture and also the focal length and wavelength. And in particular, so let's call this kind of component A in the description, but the sort of the lens diffraction limit that we have is, if we call this, so there's the pattern that we would have that was a circular function there is a Bessel function, and so there's a null around that, and there'll be a null on either side. If we blow that up, we get this 2j1x over x function. We'll derive that later, and so what I'm talking about is, that's our resolution that we'll say. There's other criteria, but we'll use that for our criteria. So our lens diffraction limit that we'll use is, if we call half of that delta x d like that to the first null on one side, the limit that we have is actually 2 delta xd, right, because we have a spot which covers that full range. 2 delta xd is going to be equal to, from the Bessel function relation, 2.44 lambda over the diameter of the lens times the focal length. So we have the f number times the wavelength times a factor of 2.44. So this just tells us what the size of the spot is as determined by the lens, all right? But now we also have another feature that we just derived, and that is the dispersion of the grating that we have. All right, so we have this grating here. So if we came in at the same angle here, right, in order for this to be satisfied at a different wavelength as we just showed, this has to shift over by some delta theta, all right? So this second, so this is, say, for lambda 1, the center of that diffraction spot. Lambda 2 is going to be off here, and this is going to be off at delta theta. We'll get a second spot, same kind of Bessel function pattern. I meant to have it the same width, but this is from lambda 2, all right? So this width that we have here is 2 delta x d. And notice you can see here, here's 1 delta x d, and here's another delta x d. So the separation between these two wavelengths is equal to this 2 delta x d. Okay, separating those two spots, those diffraction limited patterns. All right, so now what about the grating dispersion is going to determine this delta theta. All right, so we have the second part of this is, the B part is from the grating dispersion. And from that we have, we have the dispersion property of the lens, or I'm sorry, of the grating, the d theta d lambda. If we were to multiply it by delta lambda, and so delta lambda equals, lambda 1 minus lambda 2 in our case. It's just the difference between our two wavelengths that we're using. And so this then, if we have this focal length here, notice, and this is a small angle, then we can say that we have a, so this is going to give us a delta theta that we need. If we then take this delta theta, multiply it by the focal length, right, that's going to give us this is going to be equal to the separation caused by the grating. So what we need to make is this, we want to shift this over as well by a delta x g. And in order for us to distinguish these two diffraction patterns the way I've written them here, where the null of the one pattern falls on the null of the other, we have to have the condition that delta x g is greater than or equal to 2 delta x d. Okay? So again, all we're doing with this condition is we're matching the grating dispersion with the size of the diffraction limited spot that we have for that lens. We could also use mirrors too. Most spectrometers actually use mirrors in the design.
Isn't that just the Rayleigh criteria?
Well, the Rayleigh criteria is you have this dip being 88% of the separation. I chose this because I thought it was just easier to digest rather than taking a fraction of that separation. Let's just separate them totally at the first nulls. So I mean, you can distinguish things that are actually less separated than that, but I'm just choosing that, defining that.
Rayleigh and then the Sparrow. Isn't the Rayleigh, isn't that what you said? Like the peak falls on the first node?
Yeah, I think that is correct. Yeah. So there's again a number of different resolution criteria. I'm just choosing this particular one. Okay, so let's put some numbers on this to see what we can end up with. All right. So again, we'll choose that we have theta. I guess theta 1 is equal to 0 degrees, and theta 2 is equal to 30 degrees, and we'll use a base wavelength here, nominal wavelength of half a micron, and we'll just use the m equals 1, the first diffraction order. All right, so again, use our old friend here, sine theta 2 minus sine theta 1. I just flipped these in order to make it positive. You can do it the other way and use a negative order to make it work as well. That's 1 over, or the wavelength over the period. So from that we see that the period conveniently is just 1 micron in that case. And then we can determine what the dispersion of our grating is. So now the d theta d lambda is just say 1 over cosine 30 degrees times 1 over the period, and that works out to be about 1.155 inverse microns. Okay. All right, and now for the lens parameters. We'll choose the following. We have D equals 5 centimeters and focal length of 10 centimeters for an f2 system. And we have the same wavelength of half a micron. And so then we see that our 2 delta x d is equal to 2.44. 0.5 over microns over 5 centimeters times the focal length, which is 10 centimeters. So this is just equal to 2.44 microns. Okay? So now we have it, and finishing this up, we see that we have, again, we want that condition to be satisfied, all right? And so we see that we have, and the condition could be satisfied for, again, different wavelengths. The wavelengths are going to affect how much of a delta theta that we have. So again, if we have our focal length of 10 centimeters, so we have f times delta theta is now equal to 2.44 microns, then delta theta is 2.44 times 10 to the minus 5th radians, all right? And the delta lambda is delta theta over d theta d lambda, or 2.11 times 10 to the minus 5 microns, right? So that's pretty darn small, right? That's equal to 0.211 angstroms, right? Times 10 to the minus 10 meters. So we can do pretty well with a very simple system using a hologram that you guys can make actually in the lab next, during your lab 1. All right, so it's a pretty high resolution capability that you can get. Okay, so that's kind of a little introduction to dispersion, holographic element dispersion. I want to introduce you to one other thing before we move to sort of one of the main topics, and that is some of the material response characteristics. All right, so if we look at a holographic material, most holographic materials look something like this. So you have kind of a host material. It could be a polymer of some sort, or for silver halide film, it's a gelatin. And then embedded in that, there's a mixture of photosensitive sites that are embedded in that. So this is most evident, say, in silver halide, where you use very fine grained silver halide crystals. Those crystals may be on the order of 5 to 25 nanometers, rather. All right. So in this film, okay, so we'll look at some film or recording material properties. The silver halide crystals could be very small, again, 5 to 25 nanometers. Okay, the larger crystals, silver halide crystals, are faster than the smaller ones. And that's due to the fact that the exposure rate of all of these photosensitive materials are a function of the energy density. Or the joules per centimeter squared. So this is sometimes referred to as the fluence that's being used to expose the material. And the overall energy density is related to the irradiance that we have. So if we have some irradiance, illumination or irradiance, some average value of that irradiance, we get the energy by multiplying that by an exposure time, and then that's going to give us this energy density. Okay, so we'll call that RE. So when you're making a hologram, basically, what you'll be doing is measuring the irradiance. So this again is the power per unit area. Or the watts per centimeter squared that you may have. And then, so you'll be calculating, there's a specific range of exposure which is required for particular materials. And so in your case, for the polymer material that we'll be using, in the red, for instance, this optimum exposure density is around 18 millijoules per centimeter squared. Red being, say, a helium neon, 632.8 nanometer wavelength. Okay, so if we in general look at materials, so how do we get at some of these things? If we look at a material, and let's stay with silver halide material for now, for the following reason. If we look at the exposure, what happens when we expose a silver halide film? So here we'll take the log of the exposure, and here we'll have the optical density, D. This optical density, D, is equal to the log of 1 over the intensity transmittance. So if we have some material and we illuminate it, I incident, we're going to end up with I transmitted. So the intensity transmittance is equal to, say, this IT over I incidence. And so the optical density, basically it's, how black it looks, relative to a clear piece of glass. Again, we can quantify for, say, some silver halide film by looking at this plot. And this particular plot is the Herder-Drefveld. plot for characterizing, say, an absorbing material like silver halide. So if we were to look at a typical silver halide film, what we would see is the following. So there'll be some region where there's kind of a small density, residual density in that material. It's not completely clear because it has some, composition with other photosensitizing agents, which may have some residual dye and so forth in it. So it's never really 100% clear. So the optical density isn't, 0 or 1 rather, but it's some value above that. And then what happens as you keep exposing it, you then enter a linear region. And then as you keep exposing it further, it will saturate. All right. So we have this saturation region. Much like an amplifier, saturates. There's a linear region, and then it saturates. And then there's actually, we can consider this another nonlinear region, but this is sometimes referred to as the toe of this density versus log exposure curve. And then there's this linear region, which we can characterize through a slope. So it has some gamma, per unit of log exposure. And so again, so we have something here which it looks, although I didn't draw it quite linear, it is pretty linear. Now, when you remember, we have that in making a hologram, we have T. Let me use another constant, beta I, and where this I, this was equal to our R plus O squared, right? So ideally, what we want is some type of linear this is the amplitude transmittance, but you can see here that we're going to want a linear response of that material in order for us to make a hologram with good fidelity in the reconstruction. I kind of alluded to this before when we looked at if we interfere two plane waves, we end up with this cosine of phi O minus phi R as the residual term in that intensity. So if we're going to be operating out here in the saturation region, what we'll end up with are we have to do that function's going to change. It'll no longer be sinusoidal, but we're going to have other components to this description. Just like an amplifier, if you go to a nonlinear region of that amplifier, you have to have other frequency components to describe its frequency response. The same sort of thing here, except now we're looking at the density or the exposure response to that material. Okay, so ideally we want to operate in this linear region of this characteristic response. So in that linear region, all right, so we have this, again, density is equal to the log and of 1 over t. And by the way, this is base 10, not natural logarithm, but base 10. And so in this linear region, we can say that that's basically equal to the slope, right, times the x minus the intercept. So the x parameter here is log exposure, and the intercept we don't know, but it's some constant. So the intercept is going to just be a projection down there, and this is the log of k for that particular intercept. All right. So just quickly here, using our relation for logarithms, so this is going to be, again, log of e over k to the gamma, and so this is log of 1 over t, so we can also say that the transmittance function, the intensity transmittance is k to the gamma, e to the minus gamma, and this is again, just proportional to the intensity or irradiance to the minus gamma. So we end up with that the transmittance that we get after exposing this film is proportional to the intensity to the minus gamma. So what this says, I mean, this is indicating that the film responds in a negative manner. The more intensity we give it, the darker it gets. Okay, so it's going to transmit less light coming through there. So we will kind of work on this a little bit more next time. I want to talk a little bit about the Gabor hologram, which is an inline hologram, and this particular type of film characteristic has a very profound kind of effect on that inline or Gabor type hologram. So we'll talk about that a little bit next time, and then start discussing the Fourier transform relations for some of these systems that we will be looking at in the class. Okay, have a nice Labor Day weekend, and we'll see you next week.